Tonight, we're going to explore something that should, by every logic of the universe, feel completely impossible. Space is three-dimensional. It stretches infinitely in every direction: up, down, left, right, forward, backward. So here's the question that almost no one ever stops to ask. Why do all the planets in our solar system orbit the sun in nearly the same flat plane? Why not random angles? Why not one planet tumbling over the top while another cuts sideways through the middle? If you took 8 marbles and hurled them at a ball, they wouldn't magically arrange themselves into a tidy disk. And yet, our solar system looks exactly like a dinner plate with a spotlight in the center. The reason behind this is one of the most elegant stories in all of science. Before we dive in, if you enjoy these kinds of deep explorations into how the universe actually works, a quick like or subscribe would really help this channel grow. It's a small thing on your end, but it genuinely means a lot to me. Now, let's begin. Take a moment and think about the solar system the way you first learned about it in school. There's the sun in the middle, big and bright, and then there are the planets. Mercury closest in, then Venus, then Earth, then Mars, then Jupiter, Saturn, Uranus, and Neptune out at the far edge. You've probably seen the diagram 1,000 times. 8 planets stretched out in a line, all orbiting the sun, all going around in neat little loops. It's such a familiar image that almost no one stops to notice something very strange about it. Something that, when you really sit with it, becomes one of the most puzzling features of our entire cosmic neighborhood. The planets are almost all on the same flat plane. I know that probably sounds unremarkable, maybe even obvious. Of course, the planets are on a plane, you might think. That's just how solar systems work. But stop and really ask yourself why that should be true. Because when you think about it carefully, there's no obvious reason for it to be that way at all. In fact, there are 100 reasons it shouldn't be. Let me explain what I mean. Imagine you took 8 marbles and tossed them at a basketball, suspended in empty space from random directions all around the ball. If by some miracle, the basketball's gravity captured all of them, and they started orbiting, those 8 marbles would be orbiting at completely different angles. One might be going around the equator, another over the poles, another at a 45-degree tilt. It would look chaotic, messy, random, like a cloud of mosquitoes buzzing around a streetlight. That's what you'd expect in a universe where directions don't matter. And here's the thing. In space, directions genuinely don't matter. There's no up, there's no down, there's no preferred angle. When you're floating in the vacuum between stars, every direction is equivalent. Nothing in the laws of physics says that orbit should happen on a plane rather than at any other angle. Gravity pulls equally hard from every direction. An object orbiting a star can orbit it at any tilt, any inclination, any angle you can imagine, and physics is perfectly happy with that. So if the universe doesn't care about angles, why does our solar system look like a dinner plate? Because that's exactly what it looks like. If you could somehow shrink yourself down, float out beyond the orbit of Neptune, and look back toward the sun, you wouldn't see the planets scattered in a cloud around it. You would see them arranged almost perfectly along a single flat layer. It would look like someone had put the sun in the middle of a giant invisible disk, and then carefully placed each planet on that disk. Earth, Venus, Mars, Jupiter, Saturn, all of them, hovering in the same plane, circling around the sun like horses on a merry-go-round. The whole structure is shockingly, almost suspiciously flat. And it's not just that they share a plane, they all orbit in the same direction. If you were looking down from high above Earth's North Pole, you'd see all 8 planets moving counterclockwise around the Sun. Not some going one way and some going the other. Not a mix. Every single planet is moving in the same direction, on nearly the same plane, as if they're all following an invisible racetrack. That's not random. That can't be random. And the fact that it can't be random is the first clue that something very specific happened when our solar system was born. Let me give you a concrete number so you can feel just how flat the solar system really is. The orbits of the planets around the Sun are measured by something called orbital inclination. This is just the angle between the plane of a planet's orbit and the plane of Earth's orbit. Earth, by definition, has an inclination of 0 degrees because we measure everything relative to it. Now let's go through the other planets. Venus has an inclination of about 3.4 degrees, Mercury has about 7 degrees, Mars has about 1.85 degrees, Jupiter has about 1.3 degrees, Saturn has about 2.5 degrees, Uranus has about 0.77 degrees, Neptune has about 1.77 degrees. Stop and look at those numbers. Every single one is under 10 degrees. Most of them are under 2 degrees. We're talking about a whole solar system, 8 enormous worlds, spanning billions of miles, and yet they all fit within a slice of space that's narrower than the width of your thumb held up against the sky. That's not a coincidence. That's a pattern. And patterns in physics always have causes. To really appreciate how weird this is, let's compare it to what could have happened. Imagine a different kind of solar system, one where the planets orbit at random angles. Picture Jupiter cruising along at a 45-degree tilt, Saturn looping around at 80 degrees, nearly perpendicular to Earth, Mars orbiting over the Sun's North Pole. This is a perfectly valid configuration. It would obey every rule of motion and gravitation. And yet nothing remotely like this exists in our solar system. Everything hugs the same thin, invisible plate. And here's something else that makes it even stranger. This flat arrangement extends far beyond just the planets. The asteroid belt, that ring of rocky debris between Mars and Jupiter, also sits roughly on the same plane. Most asteroids orbit within a narrow band around the ecliptic. The moons of the major planets, especially the big regular moons like Jupiter's Galilean moons or Saturn's largest moons, tend to orbit their parent planets on a plane that's closely aligned with the planet's equator, which in turn is roughly aligned with the solar system's overall plane. Even the Sun itself rotates on an axis that's only tilted by about 7 degrees from the plane of the planets. It's as if somebody laid out the entire solar system on a flat surface and glued everything in place. And the thing is, no one did. There's no designer here, no cosmic carpenter with a level and a ruler. This structure had to arise on its own from the laws of physics, starting from some initial condition that somehow produced this incredible flatness. Understanding how that happened, understanding what forced this three-dimensional universe to produce a two-dimensional structure, is one of the most satisfying stories in all of science. But before we get to the answer, I want you to really feel the strangeness of the question. So let me come at it from another angle. Think about the shape of the Sun. The Sun is a sphere. It's not flat, it's round. Like every star in the universe, gravity pulls equally from every direction. And when you have a massive object with gravity acting on it, the natural shape is a sphere. That's why stars are spheres. That's why planets, once they get big enough, are spheres. That's why the moon is a sphere, and Jupiter is a sphere, and even most of the large asteroids that are massive enough to collapse under their own gravity become spherical. So if gravity produces spheres, why doesn't the solar system look like a sphere? Why isn't it a big three-dimensional cloud of planets surrounding the sun like bees around a flower? Why do we have this odd, squashed, dinner plate geometry? The answer, as we'll see, has everything to do with something that spheres don't have, but our solar system absolutely does: motion. Specifically, one very particular kind of motion. The kind that almost everything in the universe has, whether it wants to or not: rotation. But I'm getting ahead of myself. First, I want to tell you how humans figured any of this out in the first place. Because we didn't always know the solar system was flat. We had to discover it slowly over thousands of years by watching the sky very, very carefully. Let's go back thousands of years, long before telescopes. Imagine you're an ancient stargazer. Maybe you're in ancient Mesopotamia, or Egypt, or China, or Greece. You don't have any instruments. You don't have any calendars beyond what you've made yourself by tracking the sun and moon. You have your eyes, the open sky, and a lot of patience. And night after night, year after year, you and your ancestors watch the heavens. Over time, you notice something. Most of the lights in the sky, the stars, stay fixed relative to each other. The pattern of the constellations never changes. The Big Dipper looks the same tonight as it did 1,000 years ago, and it will look the same 1,000 years from now. These stars behave like lights painted on the inside of a dome, rotating as a group as the night passes. They're predictable, reliable. You can name them, group them into constellations, and tell stories about them. But there are a handful of lights that don't behave like the others. They move, slowly, over weeks and months. These strange lights drift across the background of fixed stars. Sometimes they even appear to reverse direction for a while, looping backward in a strange dance before continuing on their way. The ancient Greeks called these wanderers planets, which is where we get our word planet. And the Greeks knew of 5 of them: Mercury, Venus, Mars, Jupiter, Saturn. These were the 5 planets you could see with the naked eye, and they were known to nearly every ancient civilization that bothered to pay close attention to the sky. Now here's the important part. As ancient astronomers track these wandering lights over many years, they noticed something profound. The planets didn't wander all over the sky. They didn't go anywhere they wanted. Instead, they moved along a very specific narrow strip of sky. A highway in the heavens, if you like. A band that ran in a great circle around the celestial sphere. This band was called the ecliptic. And the ecliptic had a very particular property. It was also the path that the sun appeared to take through the sky over the course of a year. From Earth, the sun doesn't just rise and set. Over the course of 12 months, it traces out a great circle against the backdrop of stars, passing through a specific set of constellations. Those 12 constellations became known as the zodiac, and the path the sun takes through them is the ecliptic. The moon, it turned out, also travelled very close to this same path. And so did all 5 visible planets, every single one of them. This was an astonishing realization. The ancient astronomers didn't know why it was happening. They didn't know about gravity. They didn't know Earth was a planet too. They didn't know the sun was a star. But they knew, through pure careful observation, that all of these moving objects, the sun, the moon, and the planets, shared a single invisible road through the heavens. They stayed on this band of sky, and almost never strayed from it. Think about what that tells us. If the planets were orbiting at random angles, they'd appear all over the sky. Some would move through the far northern constellations. Others would pass near the southern pole. They'd be everywhere. But they weren't. They were all confined to one narrow strip. The ancients didn't have the concept, but what they had discovered, without knowing it, was the flatness of the solar system. They were looking at our plate-shaped planetary system edge on from the inside of it. And from that perspective, a flat disk looks like a narrow band going all the way around you. That's exactly what the ecliptic is. It's the edge-on view of the solar system's disk, as seen from Earth, which sits inside the disk. Every planet you can see appears to march along that band because every planet is on the same plane we are. We're not looking up at their orbits from below, or down at them from above. We're seeing them edge on, like staring across the surface of a still pond at a lily pad floating on the far side. From that viewpoint, a 2-dimensional shape collapses down and looks like a line. So when you look up tonight and spot Jupiter, or Venus shining in the morning sky, or Mars glowing red, you're seeing direct evidence of this flatness. You can trace a line through those planets and follow it across the sky, and that line is the ecliptic. The fact that the planets all sit on it is not a coincidence. It's the signature of how our solar system was born. Now, the ancient Greeks tried to explain why this pattern existed, and their best theory was a beautiful one. They imagined that the universe was made of nested crystal spheres. Earth was at the center, and around Earth were transparent celestial spheres that carried the moon, the sun, and each of the planets in circles. The outer sphere carried the fixed stars, because everything was arranged in these concentric shells, and because they rotated in specific ways, the planets appeared to move along a path rather than zooming around randomly. It was an ingenious model that did a pretty good job of describing what they saw, but it was wrong. And the reason it was wrong took over 2,000 years to figure out. When Nicholas Copernicus proposed in 1543 that the sun, not Earth, was at the center of things, he did more than just swap a few objects around. He gave us a new perspective on why the planets all share a plane. Because once you realize Earth is just another planet, also moving on the ecliptic, you realize that the ecliptic isn't some special path through the sky. It's just the flat plate we're all sitting on. Everything we see in the solar system is on this plate with us. The fact that we see the other planets, moons, and the sun all lined up along a single band in the sky is exactly what you'd expect if every significant object in the solar system is orbiting on roughly the same plane. After Copernicus, the work continued. Galileo pointed his telescope at Jupiter in 1610 and discovered that Jupiter had moons of its own, 4 little pinpoints of light that moved around the giant planet. And you know what he noticed? Those moons also orbited on a plane that was close to, but not exactly the same as the plane the planets use to orbit the Sun. It was a smaller version of the same pattern. Jupiter and its moons looked like a mini solar system, also flat, also organized along a disk. When astronomers studied Saturn's rings, they found the same thing. Saturn's rings are perhaps the most dramatic example of this flatness in the entire solar system. They're literally a disk. Not metaphorically, not sort of. They are a real, physical, flat disk made of billions of chunks of ice and rock orbiting Saturn. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. And yet, they span tens of thousands of miles across. That's an extraordinary shape. Not a sphere, not a cloud, but a razor-thin disk. By the time telescopes had improved enough to see the outer planets clearly, the pattern was undeniable. Everywhere you looked in the solar system, wherever you found a massive object with things orbiting it, those orbits formed flat structures. Planets around the Sun, moons around planets, rings around Saturn, asteroids in the asteroid belt, even the dust and debris that swirls between the planets. Flatness everywhere. And this wasn't just true of our solar system. Once humans got really good telescopes, really advanced instruments, and once we turned them on other stars, we start to see similar flat structures around young stars all over the galaxy. There are places in space where new stars are forming right now, and around those new stars we could see enormous disks of gas and dust. We call these protoplanetary disks. They're factories for new solar systems, and they're always flat. Always. We've observed dozens of them directly with instruments like the Hubble Space Telescope and the ALMA Radio Telescope Array in Chile, and every single one of them shows the same geometry. A young star in the middle, a flat rotating disk of material spread out around it, and sometimes even gaps carved in the disk where baby planets are forming. Flatness appears to be fundamental, not a quirk of our solar system, not a lucky accident, but a universal feature of how planetary systems come into being. So here we have a mystery. A universe where every direction is supposed to be equivalent produces, over and over again, these incredibly flat arrangements. Stars around, planets around, moons around. But the systems they form together are flat. Why? That's the question that's been lingering in the background of everything we've discussed so far. And notice that I haven't answered it yet. I've shown you the evidence. I've shown you how humans slowly piece together the pattern over centuries of observation. I've shown you how ancient astronomers spotted the narrow band of sky we call the ecliptic without knowing what it meant. I've shown you how Copernicus and Galileo and later astronomers revealed that the pattern isn't just above our heads, it extends everywhere, down to the moons of Jupiter and the rings of Saturn, and out into the disk of baby stars forming on the other side of the galaxy. But I haven't told you why it happens, because to answer that, we have to talk about how our solar system actually began. And our solar system did not start as a star with planets around it. It didn't start as anything you would recognize. Long before the sun existed, long before Earth was even a thought, there was a cloud. An enormous, cold, dark cloud of gas and dust drifting through the galaxy. That cloud had nothing special about it. It was just one among many. Clouds like this float between the stars, invisible to the naked eye, silent and slow and patient. And inside that cloud, something was hiding. Something so small and so subtle that you'd never notice it if you were floating through the fog. But it was the single most important ingredient in the entire story. It was what would eventually turn a formless cloud into a flat disk, and then a flat disk into a solar system, and then a solar system into a place where, billions of years later, a species called humans would look up at the sky, trace the path of the planets, and wonder why everything they could see was lined up along a single band across the heavens. Before we go further, I want to tell you something remarkable about how we know what happened to our specific solar system. Because you might be wondering how we can possibly know any of this. It all happened 4.5 billion years ago, long before anyone was around to see it. How can scientists be so confident about the details? The answer is that the evidence is still here. It's in the rocks. Specifically, it's in meteorites. The oldest meteorites that have fallen to Earth are leftover scraps from the very first days of the solar system. They're debris that never got incorporated into any planet, and they've been floating around essentially unchanged ever since they formed. When we cut them open and examine them under microscopes, we find little round structures called chondrules and weird crystal clumps called calcium-aluminum inclusions. These are some of the oldest solid objects in the entire solar system. We can measure their ages using radioactive dating, and they consistently come out to about 4.5 billion years old. Specifically, about 4.57 billion years. That's the age of our solar system. We know it with extraordinary precision because the rocks themselves are telling us. But here's the really amazing part. When scientists analyzed the chemical composition of these ancient inclusions, they found something unexpected. The inclusions contain evidence of certain radioactive isotopes, like aluminum-26 and iron-60, that have very short half-lives. These isotopes decay so quickly that they couldn't have existed in the cloud for long before it collapsed. These isotopes are produced in large quantities primarily by the explosions of massive stars, supernovae. So the very presence of these isotopes in our oldest meteorites is telling us that a supernova went off near our pre-solar cloud, and that its shockwave probably triggered the collapse of our solar system. The fingerprint of that supernova is preserved in stones that landed on Earth billions of years after the event. Someone had to come along much later, pick up those stones, slice them open, and read the story they contained. We are quite literally reading the birth certificate of our solar system in the rocks. That hidden ingredient is the key to everything. It's the reason our solar system is flat instead of round. It's the reason the planets share a plane, and share a direction, and travel along the ecliptic like beads on a string. And it's about to transform a vast, dark, lazy cloud of gas into the most remarkable piece of cosmic engineering imaginable. To understand how, we first need to follow that cloud on its journey. We need to watch as gravity reaches in, gives it a gentle push, and starts a process that cannot be stopped. A process that begins in darkness, gathers speed, and ends in fire and light. A process that will take a formless object and give it a shape. Not any shape, but the very specific shape we see today when we look out across the sky and notice that all the planets somehow, mysteriously, impossibly, are in line. To understand where our solar system came from, we have to travel back in time. Not a little bit. A lot. We have to go back more than 4.5 billion years. To a time before Earth existed. Before the sun existed. Before any of the planets you can name. Before the moons of Jupiter. Before the rings of Saturn. Before any of it. And what we find when we go back that far is not a smaller version of our solar system. It's not a bright young sun with a few baby planets around it. It's nothing like that at all. It's a cloud. A vast, dark, cold, silent cloud of gas and dust drifting through the galaxy. Now, when I say cloud, I don't want you to picture the kind of cloud you see in the sky on a summer afternoon. That's a very different thing. A cloud on Earth is made of tiny droplets of water suspended in air, and it's relatively small, and it's held together by the atmosphere of our planet. What I'm talking about is something on an entirely different scale, made of entirely different stuff, and existing in an entirely different place. The clouds I'm describing are called molecular clouds, and they are some of the largest single objects in the entire galaxy. Molecular clouds are made mostly of hydrogen, the lightest and most common element in the universe. About 74% of the mass of any molecular cloud is hydrogen. Another 24% or so is helium, the second simplest element. And then, the last couple of percent is everything else. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements, most of them in tiny concentrations. These heavier elements are important, even though they make up almost none of the total mass, because they include the building blocks of planets and of life. Every atom of iron in your blood, every atom of calcium in your bones, every atom of carbon in the cells of your body came originally from a molecular cloud, very much like the one that formed our solar system. You are, quite literally, made of the same stuff as these interstellar clouds. We'll come back to that later. Alongside the hydrogen and helium, there's also something called interstellar dust. Now, dust is another word that might mislead you. When you think of dust, you probably picture the stuff that settles on your bookshelves, or the fine particles that dance in a sunbeam coming through a window. Interstellar dust is not that. It's much smaller. Interstellar dust grains are tiny solid particles, usually no bigger than a micron across, which is about 1/100th the width of a human hair. They're made of things like silicates, which are rocky minerals similar to what you'd find in sand or stone, and complex carbon compounds, and sometimes ice is made of frozen water or carbon dioxide or methane. These dust grains are critically important, because even though they make up only about 1% of the total mass of a molecular cloud, they're what gives the cloud its character. They block light, they cool the gas, and later on, they'll clump together and form the seeds of planets. How big are these molecular clouds? Absolutely enormous. A typical molecular cloud might be anywhere from a few light years to hundreds of light years across. Remember, a light year is the distance light travels in a single year, which is about 6 trillion miles. So we're talking about clouds that span trillions upon trillions of miles. The biggest molecular clouds, called giant molecular complexes, can contain enough gas and dust to eventually form millions of stars. They are, in a real sense, stellar nurseries. Every star you see in the night sky was born inside of one of these clouds. And how dense are they? This is one of the most counterintuitive things about molecular clouds. Even though they're enormous, they're also almost perfectly empty. In the densest parts of a molecular cloud, you might find about 1 million particles per cubic centimeter. The air you're breathing contains roughly 25 quintillion. A molecular cloud is trillions of times less dense than the atmosphere you're sitting in. A vacuum more perfect than anything that can be manufactured on Earth. And yet, when you have enough of this nearly empty gas spread over hundreds of light years, it adds up to a staggering amount of material. Enough to make stars by the thousands. Enough to make planets. Enough, eventually, to make a world like ours, and a species like ours, and a mind like yours, listening to this. These clouds are also incredibly cold. The average temperature inside a molecular cloud is around 10 Kelvin, which is about minus 263 degrees Celsius. That's colder than anything that exists naturally on Earth. It's only about 10 degrees above absolute zero, the coldest temperature that is physically possible anywhere in the universe. At those temperatures, the atoms in the cloud move very slowly. They don't have much energy, and that, as we'll see, turns out to be important. Cold clouds can collapse, hot clouds can't. The coldness is what makes the story possible. And they're dark. Really, truly dark. Molecular clouds are so thick with dust that almost no visible light can penetrate them. If you were sitting inside one, you couldn't see anything. You wouldn't even see the stars on the other side of the galaxy. The dust grains absorb and scatter visible light, trapping it. This is why, when astronomers first started photographing the Milky Way, they noticed these strange dark patches scattered across the bright band of stars. For a long time, people thought the dark patches were holes in the galaxy, places where there just happened to be no stars. But they're not holes. They're clouds, opaque curtains of dust and gas, hiding whatever is behind them. If you want to see one for yourself, go look up at the Milky Way on a clear night in a dark location, and you'll notice a large dark rift running down the middle of the band of light. That's not empty space. That's a lane of dust and gas stretching across our galaxy, blocking the light of the stars behind it. Right there, visible to the naked eye, you're looking at raw material for future stars and planets. Astronomers have spent decades studying these clouds, and one of the most famous examples is the Orion Nebula. If you go outside on a clear winter night and find the constellation Orion, with its 3 bright stars in a row forming the belt, look just below the belt. You'll see what appears to be a fuzzy star hanging from the belt like a sword. That fuzzy patch is not a star, it's a nebula. A giant cloud of gas and dust about 1,300 light-years away from Earth. It is one of the nearest stellar nurseries to our planet, and right now, as you hear this, new stars are being born inside it. The Orion Nebula is roughly 24 light-years across, which means if you could travel through it at the speed of light, it would still take you 24 years to cross from one side to the other. And inside that cloud, astronomers have directly observed hundreds of young stars in various stages of formation, each one surrounded by its own disk of gas and dust. Each one is a miniature version of what our solar system looked like 4.5 billion years ago. Another famous example is the Eagle Nebula, home to the Pillars of Creation. Those towering columns of dust and gas, made famous by the Hubble Space Telescope's photographs, are regions inside the Eagle Nebula where new stars are actively forming. The pillars are enormous. The tallest of them is about 4 light-years from top to bottom. That's longer than the distance between our sun and the nearest star. And what you're seeing in those images, though it doesn't look like much more than clouds of glowing gas, is actually the birth process itself. Denser regions within the pillars are collapsing under their own gravity, forming cores that will eventually become new stars. Telescopes sensitive to infrared light, which can penetrate the dust that visible light cannot, have already detected hundreds of baby stars inside these pillars. Each one is following exactly the same process our sun followed. A cloud, a collapse, a spin, a disk, star after star, system after system, born the same way. And here's something fascinating. We don't just look at these clouds with ordinary telescopes that detect visible light. Visible light can't penetrate the dust of a molecular cloud, remember? So we'd be completely blind to what's going on inside if we only had our ears. But astronomers have built telescopes that detect other kinds of light. Infrared light, which is longer wavelength than visible light, can slip through the dust more easily. Radio waves, which are longer still, can pass through almost unobstructed. So when we point infrared telescopes like the Spitzer Space Telescope, or its successor the James Webb Space Telescope, at a molecular cloud, suddenly we can see inside. The dark curtains part and we see the hidden newborn stars glowing in the infrared. And when we point radio telescopes like the ALMA array in Chile at these clouds, we can actually map out the distribution of molecules inside them. We can trace where hydrogen is clumping together, where carbon monoxide is flowing, where dense cold regions are preparing to collapse. We can essentially watch the birth process happening step by step, in real time, across hundreds of different clouds, at different stages of the process. So now we have a picture of where our solar system began, not as a star, not as a planet, not as anything you would recognize, but as part of a vast, cold, dark, quiet cloud of gas and dust drifting through the galaxy for millions of years, maybe tens of millions of years. This cloud just existed. It didn't do anything dramatic. It just hung there, slowly moving along with the gentle rotation of the galaxy, its particles bumping into each other almost never, its temperature remaining cold and steady, its gravity holding it together in the loosest possible way. But here's the thing about molecular clouds. They don't just sit around forever. Something eventually happens to them. And that something is what begins the story of our solar system. Let me explain what I mean. A molecular cloud in its normal state is in a kind of delicate balance. On one hand, gravity is always trying to pull it together. Every atom of hydrogen, every speck of dust is gravitationally attracting every other atom and speck in the cloud. That attraction, spread over trillions of miles and countless particles, adds up to a real force that wants to collapse the cloud into something smaller and denser. On the other hand, there are forces pushing back. The cloud has some internal pressure from the movement of its particles, even at those cold temperatures. It has turbulence, little currents of gas flowing in various directions. It sometimes has magnetic fields threading through it, which resist compression, and it has the gentle rotation of the galaxy carrying it along, which provides a kind of orbital support against collapse. For a long time, these outward forces balance the inward pull of gravity, and the cloud just sits there. But it's a fragile kind of balance. It only takes a small push to tip the scales in gravity's favor and set off a chain reaction. What could provide that push? Several things. The most common, and probably the one that affected our solar system, is a shock wave from a nearby supernova. A supernova is what happens when a massive star runs out of fuel and explodes. The explosion is one of the most violent events in the universe, briefly outshining entire galaxies and releasing more energy in a few seconds than the sun will release in its entire life. When a supernova goes off, it sends out a wall of material and radiation traveling outward at tremendous speeds. If a nearby molecular cloud gets hit by that shockwave, the sudden pressure compresses part of the cloud, making it denser and tipping the gravitational balance in gravity's favor. Once gravity wins, the region that was compressed begins to collapse inward on itself. Another way a cloud can be triggered to collapse is by a close encounter with another star. Stars in the galaxy are usually very far apart, but the galaxy is old, and over billions of years, stars occasionally come close to each other. When a star passes near a molecular cloud, its gravity can disturb the cloud, squeezing some regions and stretching others, and once again tipping parts of the cloud into collapse. Sometimes, spiral arms of the galaxy itself can compress the cloud. The Milky Way has these beautiful spiral structures, and as clouds drift into a spiral arm, they encounter higher densities of gas and dust there, which can trigger collapse in the denser regions. Whatever the trigger, the result is the same. Part of the cloud crosses a critical threshold. The inward pull of gravity overwhelms the outward forces holding it up, and the region starts to collapse. Gas and dust that had been floating freely for millions of years suddenly begins to fall inward, drawn toward a center of mass. And once collapse begins, it doesn't stop. It accelerates. Here's why. As gas and dust fall inward, the density in the central region increases. Higher density means stronger gravity pulling on the surrounding material. Stronger gravity means faster infall. Faster infall means even more material piling up in the center, which means even higher density, which means even stronger gravity. It's a runaway process. Once it starts, it feeds on itself. The cloud, which had been placid and unchanging for ages, now begins to contract faster and faster, pulling in material from greater and greater distances. A region of the cloud that had been light years across starts shrinking down into something smaller, and smaller, and smaller. This is the beginning of the story. This is the moment our solar system started becoming our solar system. 4.5 billion years ago, somewhere in a vast molecular cloud in our galaxy, a region began to collapse. It might have been triggered by a supernova shockwave. In fact, astronomers have found chemical evidence in ancient meteorites, suggesting that a supernova did explode not far from our pre-solar system cloud, and that its shockwave may have been what set the whole process in motion. But regardless of the exact trigger, something happened. A region of the cloud started to fall inward, and once it did, there was no going back. Now here is where we get to the single most important property of the original cloud. The property that will determine the final shape of our solar system. The property that makes everything else in this story possible. Rotation. Every molecular cloud rotates. Not because anyone spun it on purpose, not because there's some special force in the universe that makes things spin, but because the universe is a big, complicated, turbulent place, and almost nothing in it is truly, perfectly, absolutely still. Every cloud of gas has some motion. Some parts of it drift one way, other parts drift another way. The cloud as a whole turns, very slowly, because the galaxy itself is turning, and because the cloud has been jostled and pushed and nudged by countless interactions over millions of years. The rotation might be extremely slow, so slow that if you were sitting inside the cloud, you'd never notice it. It might take millions of years for the cloud to turn once, but here's the thing. Slow rotation is still rotation, and rotation, once you have it, is a very stubborn thing. In physics, we have a concept called angular momentum. Angular momentum is the measure of how much rotation an object has. And one of the deepest laws in all of physics is that angular momentum is conserved. You cannot create it out of nothing. You cannot destroy it. If an object has rotation, that rotation stays with it unless some outside force takes it away. This is called the conservation of angular momentum, and it's one of the most important ideas we'll talk about tonight. Because what it means is this: if a big cloud of gas is rotating slowly, and then that cloud collapses and gets smaller, it cannot simply stop rotating. The rotation has to go somewhere. and the only place for it to go is into faster spinning. A smaller rotating object spins faster than a larger rotating object with the same angular momentum. Always. Without exception. You've actually seen this principle demonstrated many times, probably without realizing it. Think about a figure skater doing a spin on the ice. When the skater starts spinning, her arms are outstretched, and she rotates at a certain speed. But then she pulls her arms in, close to her body, and suddenly she's spinning much faster. So fast that she becomes a blur. She didn't push off the ice harder, she didn't use her muscles to accelerate. All she did was change her shape. By pulling her mass closer to her center, she forced herself to spin faster. That's angular momentum conservation in action. The total amount of rotation had to stay the same, so when the skater's body got smaller, her spin rate went up. Now imagine a cloud of gas, trillions of miles across, rotating extremely slowly, once every few million years. And now imagine that cloud collapsing. Not just shrinking a little bit, but collapsing from trillions of miles across down to a region only billions of miles across. Then hundreds of millions of miles, then millions of miles. That's a reduction in size by an enormous factor, and every time the cloud gets smaller, its rotation speeds up. By the time the collapsing region has shrunk to a fraction of its original size, it's spinning thousands or millions of times faster than it was when it started. What began as an almost imperceptible drift becomes a rapid whirl. The original cloud had to have some rotation, even if tiny. And now, as it collapses, that tiny rotation is being amplified, compressed, and concentrated. The pre-solar cloud is beginning to spin, not gently, not lazily, but fiercely. And the faster it spins, the more important its rotation becomes. Because rotation, as we'll see, does something very specific to a collapsing cloud. It prevents it from collapsing evenly in all directions. It creates a preferred axis, and along that axis, strange things start to happen. But before we get to that, I want to pause and make sure you've really absorbed the picture so far. We have a cloud. Cold, dark, huge, nearly empty. It's been drifting through the galaxy for millions of years, doing nothing. Then something happens. A nearby supernova, a passing star, a spiral arm of the galaxy, whatever it is, a disturbance gives the cloud a push, and a region inside it begins to collapse. Gravity takes over, and the region starts falling inward. As it falls inward, it gets smaller and denser. And because the original cloud had some rotation, that rotation is amplified by the collapse. The shrinking region begins to spin, faster and faster as it contracts. What we have now is not a cloud anymore, or not exactly. It's something in transition. A collapsing, rotating blob of gas and dust, getting denser by the minute, spinning faster by the minute, heating up at its center, and moving inexorably toward a new shape. Not the shape of the original diffuse cloud, not the shape of a final solar system. Something in between. Something that's being forced into existence by the combination of two forces. Gravity pulling everything inward, and rotation, forcing everything to swing around a center. Let me give you a sense of the time scale here. The collapse of the pre-solar cloud didn't happen overnight. It didn't happen in 1,000 years. It didn't even happen in 100,000 years. The initial collapse phase, where the cloud contracts rapidly into a dense core, probably took somewhere between a few 100,000 and 1,000,000 years. Full ignition of sustained hydrogen fusion came later, after the protostar had finished contracting over tens of millions of years. That sounds like a lot by human standards. But compared to the age of the universe, or even compared to the age of the galaxy, it's practically instantaneous. The collapse of a cloud into a star is a violent, rapid event on cosmic timescales. One moment you have a cloud, a blink of the galactic eye later, you have a star. The first major stage of this process, called the free fall collapse, is when the cloud is contracting most rapidly. The gas is falling inward under gravity, nothing is yet resisting it strongly, and the density at the center is shooting up. This stage can last maybe a few tens of thousands of years. Then the center gets dense enough that it becomes opaque to its own radiation. Heat can no longer escape easily, and the core starts to heat up dramatically. This is when the protostar begins to form. The protostar is not yet a true star. It's a dense, hot ball of gas that's still contracting, still accumulating material from the surrounding cloud, but not yet fusing hydrogen into helium. The protostar phase can last anywhere from 100,000 to a few million years, depending on the mass of the collapsing cloud. Smaller clouds take longer, bigger clouds collapse faster. During the protostar phase, the young sun went through a stage astronomers call the T-Tauri phase. This is a particularly chaotic period in the life of a young star. The star is still growing, still pulling in material from its surroundings, but it's also throwing off huge amounts of material in powerful jets and winds. A T-Tauri star is a turbulent, flaring, unstable object that can change its brightness significantly over the course of just days or weeks. We've directly observed T-Tauri stars throughout our galaxy. They're in the Orion Nebula, in the Taurus star-forming region, in many other places. Every one of them is a living example of what our sun looked like when it was young. 4.5 billion years ago, our sun was a T-Tauri star, blasting out powerful solar winds, still surrounded by the cloud of gas and dust from which it was born. And it was in those chaotic early days that the disk around it was taking shape, setting the stage for everything that would come next. These two forces, gravity and rotation, are about to have a fight. Gravity wants the cloud to be a sphere. It pulls equally hard in every direction. So if gravity were the only force involved, the result would be a big round ball of gas with a star at the middle and nothing else. But rotation doesn't want a sphere. Rotation wants to fling things outward, perpendicular to the axis of spin, and the faster the rotation, the stronger that outward fling. What happens when these two forces meet? That's where the magic is. That's where the flatness comes from. That's where our solar system gets its shape. And we're going to get there soon. But first, there's one more thing I want you to understand about the collapsing cloud. Because the collapse isn't gentle. It isn't tidy. As the cloud falls inward, the center of it, the place where most of the gas is piling up, starts getting hot. Really hot. Here's why. When gas falls inward under the force of gravity, it gains kinetic energy, which is just the energy of motion. And when gas particles moving fast bump into each other, that kinetic energy gets converted into heat. It's the same reason a meteorite heats up when it falls through Earth's atmosphere. The falling gas is being squeezed tighter and tighter in the center, and all the energy of its infall is being converted into thermal energy. The temperature rises. From 10 degrees above absolute zero, the center of the collapsing cloud heats up. First to a few hundred degrees, then thousands, then tens of thousands, then hundreds of thousands, and eventually millions of degrees. At some point, which might be anywhere from 100,000 to 1 million years after the collapse first began, The center of the cloud becomes so hot and so dense that something extraordinary happens inside it. Nuclear fusion begins. The hydrogen atoms in the core start slamming together so violently that they fuse into helium, releasing enormous amounts of energy in the process. A new star has just been born. In our case, it was the Sun. But here's what's important for our story. The Sun, massive as it is not the end of the process. The Sun, at the very center, holds about 99.8% of the mass of the new solar system. But that leaves about 0.2% of the original cloud that didn't fall all the way into the Sun. That 0.2% is still out there, surrounding the young Sun. It's still falling inward, still spinning, still governed by all the same forces that we've been talking about. And that 0.2%, tiny as it sounds, is enough to make every planet, every moon, every asteroid, every comet, and every ring system in our solar system. Everything you see when you look up at the night sky that isn't a star was made from that leftover material. Now, what's happening to that leftover material is the heart of this whole story, because it's not just hanging there motionless around the Sun, it's been spinning too. It inherited the rotation of the original cloud, and that rotation is getting faster as things contract. And the moment you have a large amount of gas and dust spinning rapidly with gravity pulling it toward a central object, you are about to witness something that physics insists must happen. Something so universal, so inevitable, that we see it every time we look at a young star system anywhere in the galaxy. A cloud of matter, given rotation, cannot stay a cloud. It cannot stay round. It is forced by the laws of nature to flatten, to become a disk. How that happens, why a rotating cloud has no choice but to collapse into a thin, flat, rotating plate, is the single most important mechanism in our story. It's what takes a three-dimensional cloud and turns it into a two-dimensional disk. It's why the planets, when they eventually form, all end up on the same plane. It's the answer to the question we started with. And it's what we're going to explore next. So here we are. We have a young sun at the center, burning its way into existence through nuclear fusion. And around it, we have the leftover material. That tiny 0.2% of the original cloud that didn't fall all the way in. Gas and dust, still spinning, still under gravity's pull, still governed by the laws of physics. And now we come to the question that's been waiting for us this entire time. Why does that material, which could in principle arrange itself into any shape, end up as a flat rotating disk? The answer is one of the most elegant pieces of physics in the entire story of our cosmic origins. It's a consequence of something so fundamental, so universal, that once you understand it, you realize it couldn't have happened any other way. A rotating cloud of gas and dust must flatten. Not might. Not sometimes. Must. And the reason why is something we can work out together right now, from first principles, using only things you already intuitively understand about how the world works. Let me start by setting the stage. Imagine you could pause time for a moment and float out into the young solar system. Just as the sun is igniting and the leftover material is swirling around it. What would you see? You'd see a rough, cloudy sphere of gas and dust with a brilliant star at the center. The cloud wouldn't be perfectly spherical because rotation has already squashed it a bit, but it wouldn't be a flat disk yet either. It would be more like a fat pumpkin or a thick lens, something in between a ball and a plate. The question is, how does that pumpkin become a plate? To answer that, we have to follow the gas, not as a whole, but particle by particle. Because the key to understanding the flattening is realizing that different particles in the cloud are moving in different ways, and those different motions have very different fates. Let's pick an imaginary axis of rotation. This is just the axis around which the whole cloud is spinning. Think of it like a tall, invisible pole, running straight up through the sun. Everything in the cloud is turning around this axis. Some particles are turning near the axis, some are turning far from it, but all the rotation is happening around this one invisible line. Now, any particle in the cloud, any single atom of hydrogen or speck of dust, is doing two things at the same time. First, it's being pulled inward by the gravity of the young sun. Second, it's moving in some direction due to its own motion within the cloud. That motion can be broken down into two components. One component is motion perpendicular to the axis, which is the motion that carries the particle around in a circle. This is the rotational motion. The other component is motion parallel to the axis, which is motion up and down along the axis. This is the motion that would take a particle from the top of the cloud toward the bottom, or from the bottom toward the top. Every particle has some mixture of these two kinds of motion. Some particles are mostly moving around the axis, others are mostly moving up and down along the axis. Most are doing some combination of both. And the question is, what happens to each of these motions as the cloud evolves? Because it turns out they have very different fates. Let's start with the motion along the axis, the up and down motion. Imagine you're a particle in the cloud, and you happen to be moving downward along the axis. You're heading from the top of the cloud toward the middle. Now, somewhere above you, there's another particle that was moving upward, from the bottom of the cloud toward the middle. The two of you are on a collision course. You're moving toward each other along the axis of rotation. What happens when you collide? Well, in physics, when two particles smash into each other head-on with opposite motions, their motions tend to cancel out. It's like two cars hitting each other head-on at the same speed. The combined result is that both cars come to a stop. Their individual motions, which were in opposite directions, cancel. The energy of that collision doesn't just vanish, it gets converted into heat and into deformation of the cars. But the motion, the thing that was carrying them in opposite directions, that gets neutralized. The same thing is happening throughout the cloud. Particles moving up along the axis are colliding with particles moving down along the axis. The collisions cancel their vertical motion, and the kinetic energy becomes heat. The heat then radiates away as light, disappearing into the surrounding space. So vertical motion gets washed out. It gets eroded by collisions. Over time, with enough of these collisions, the average up and down motion in the cloud approaches zero. The cloud gets thinner along the axis of rotation, because there's no longer any net motion holding particles up or down. Now think about what happens to the rotational motion, the motion around the axis. Here's the crucial difference. All of the particles that are going around the axis are going in the same direction. That's what rotation means. They're all sweeping through circular paths, all in the same rotational sense. Some are going in slightly tilted planes, some are in slightly different orbits, but the overall sense of motion around the axis is the same. When two particles going in the same rotational direction collide, their motions don't cancel. Instead, they average out. The faster particle loses a little speed, the slower one gains a little, but they keep moving in the same direction. The rotation survives the collision. This is the fundamental asymmetry at the heart of everything. Motion along the axis gets cancelled out by collisions, because opposite motions meet each other. Motion around the axis survives collisions, because all the motion is in the same direction. So as the cloud evolves and particles keep bumping into each other, one kind of motion disappears while the other stays intact. Vertical motion dies, rotational motion lives. And that's the mechanism. That's it. That's the whole reason our solar system is flat. Because collisions in a rotating cloud preferentially destroy the motion perpendicular to the rotation axis, while leaving the motion around the axis more or less untouched. So over time, the cloud gets thinner and thinner along the axis of rotation, while retaining its full extent in the plane of rotation. A three-dimensional cloud gradually squashes itself into a two-dimensional disk. Now, I've been using the word collision, but I should be a little more careful about what I mean. In a gas, individual atoms are bumping into each other constantly, but the effect is the same at every scale. Small clumps of gas run into other small clumps. Streams of gas shear against each other and create turbulence. Dust grains get dragged along with the gas and occasionally slam into each other. All of these interactions act like friction. They redistribute energy. And at every scale, the same asymmetry applies. Motions that oppose each other cancel out. Motions that are all in the same direction survive. This is sometimes called viscosity, or just friction, and it acts throughout the entire cloud. The net effect is that the cloud flattens. Its vertical extent shrinks dramatically, while its horizontal extent stays about the same. Over time, it goes from being a squashed sphere to a thick lens to a thin plate. How thin? Astonishingly thin. By the time the flattening process is complete, the disk of gas and dust around a young star is typically several hundred astronomical units across, but only a small fraction of that in thickness. The disk is thinnest near the star and gradually flares outward, becoming slightly thicker at its outer edges. Even at its thickest point, the ratio of width to thickness is enormous. If you scaled the whole disk down to the size of a large pizza, you'd have to make the pizza hundreds of times wider than it was tall. It's more like a sheet of paper than a plate. We have direct evidence of this. Astronomers have observed disks like this around young stars throughout the galaxy. When the Hubble Space Telescope turned its gaze toward the Orion Nebula back in the 1990s, it captured dozens of these disks, each one surrounding a baby star, each one appearing as a flat dark silhouette against the bright background of the glowing gas behind it. They even got a nickname, Proplids, short for protoplanetary disks. They are flat, unmistakably flat. Thin, rotating structures of gas and dust spread out around newborn stars. Exactly what physics says should form when a rotating cloud collapses. The ALMA telescope, which stands for the Atacama Large Millimeter Array, has given us our clearest views yet of these disks. ALMA is located high in the Atacama Desert in Chile, at an elevation of about 5,000 meters, where the dry, thin atmosphere allows it to detect the faint radio waves emitted by cold dust and gas in distant disks. The array consists of 66 separate radio dishes that work together to produce images with extraordinary resolution. And when ALMA turned its attention to a young star called H.L. Tauri in 2014, it took one of the most important images in the history of astronomy. The H.L. Tauri image shows a flat disk of gas and dust, about 150 astronomical units across, surrounding a young star that's only about 1 million years old. That's extraordinarily young by stellar standards, roughly comparable to what our sun was like during its earliest days. What makes the image so striking is that the disk isn't a smooth, featureless plate. You can see concentric rings and gaps etched into it, like grooves on a vinyl record. The rings are bright, the gaps are dark, and they're arranged in a beautiful pattern stretching outward from the central star. Astronomers are still debating exactly what's carving those gaps, but the leading explanation is that baby planets are already forming inside them. Each gap marks a place where a growing protoplanet is sweeping up material from the surrounding disk, clearing a path as it orbits. In other words, we are looking at planet formation in progress, right now, happening around a star only 450 light-years away. And HL Tauri is not unique. Another famous disk is around the star Beta Pictoris, about 63 light-years from Earth. The Beta Pictoris disk is a bit older and more evolved than HL Tauri's, and we can see it almost edge on, so it appears as a thin, bright line extending out from the star. Astronomers have detected a massive planet orbiting within that disk, and they've even seen evidence of comet-like bodies falling into the star. Beta Pictoris is like a snapshot of what our solar system looked like a few tens of millions of years after it formed, after the planets had started to clear out their orbits, but before the disk had completely dissipated. Systems like these are giving us a living laboratory to study planetary formation, and in every single one of them, the fundamental structure is the same. A central star, a flat rotating disk, planets forming along the disk's plane. The pattern holds universally. The ALMA telescope in Chile has since imaged many of these disks in even more detail. One of the most famous is around a young star called HL Tauri. The image ALMA took in 2014 is extraordinary. It shows a flat disk of gas and dust, and within that disk, you can see concentric rings and gaps. Those rings and gaps are almost certainly being carved by baby planets already forming inside the disk. But notice the geometry. The planets are forming in a disk, a flat disk, the same kind of disk that must have existed around our sun 4.5 billion years ago when our own planets were being born. Let me go back and make sure I've communicated why this happens, because it's so central to everything. Imagine you have a cloud of gas that is completely random in its motion. Every particle is going in some direction, and there's no overall pattern. Is there any preferred direction in this cloud? No. It's symmetric. It looks the same from every angle. But now suppose you give the whole cloud just a tiny bit of rotation. Maybe 99% of the motion is still random, and only 1% is coherent rotation. Does that tiny bit of rotation matter? Surprisingly, yes. It matters enormously. Here's why. Over time, collisions between particles will cancel out the random motions. Two particles moving in opposite random directions will smash into each other, and their motions will average out. Eventually, through countless collisions, all the random motion gets erased. But the 1% of coherent rotation, the bit where everything is spinning around a common axis, doesn't cancel. It survives. Because it's coherent. Because it's organized. Because every particle participating in it is moving in a way that doesn't cancel with the others. So as collisions keep happening, the random motion gets smoothed away, and what's left is the rotation. The cloud, which started out mostly random with just a hint of rotation, ends up being dominated entirely by rotation, and the rotation defines an axis, and along that axis, collisions have cancelled out all the motion, so the cloud becomes thin along the axis. And the cloud keeps its width perpendicular to the axis, where the rotation is carrying particles around. The result is a flat, rotating disk every single time. It's unavoidable. Now, one thing I want to emphasize is that this happens even if the original cloud had only a tiny, tiny amount of rotation to start with. It doesn't need to be spinning fast. It doesn't need to be obviously rotating. Even an almost imperceptible spin, stretched out over millions of years, is enough. Because as the cloud collapses, that tiny spin gets amplified by angular momentum conservation. The cloud starts spinning faster and faster as it shrinks, and once it's spinning fast enough for rotation to dominate over random motions, the flattening begins. In other words, the universe doesn't need any special initial conditions to produce a flat solar system. It just needs a cloud with some rotation, any rotation at all, and gravity to pull it inward. The rest is automatic. Flatness is not a rare outcome. It's not a special arrangement. It's the default. It's what happens whenever the ingredients come together, which is why we see it everywhere. There's another way to think about this. Imagine a pizza maker spinning dough in the air. The dough flattens out because the part moving with the spin gets flung outward, while the parts along the axis of spin get pulled inward. After enough tosses, you've got a flat crust instead of a ball. That's exactly the physics at work in a collapsing cloud. Rotation flings material outward in the plane perpendicular to the axis. Gravity and collisions pull material inward along the axis. The combination turns a three-dimensional blob into a two-dimensional disk. Except on a much larger scale. Much larger. Our early solar system disk was about 200 astronomical units across, which is 20 billion miles. And it was rotating, and it was collapsing, and it was flattening, and over something like 100,000 years, it went from a squashed cloudy blob to a thin spinning disk. And that disk, called the solar nebula, was the structure inside which every planet in our solar system would eventually form. Let me say a bit more about what this disk was like, because it wasn't just a uniform plate of matter. It had structure. Different regions of the disk had different properties, and those differences mattered a lot for what kinds of planets would eventually form in each region. Close to the young sun, the temperature in the disk was extremely high, thousands of degrees. So hot that volatile materials like water, methane, and ammonia couldn't exist as solids or even liquids. They were vaporized. Only the hardiest materials could remain solid in that environment. Things like iron, nickel, silicates, and rocky minerals. So the inner part of the disk was dominated by solid grains of rock and metal, floating in a hot gas. Farther out, away from the sun's intense heat, the temperature dropped. At a certain distance, water ice could exist as a solid. Farther still, other volatiles could freeze. The outer parts of the disk were cold and icy, full of frozen water, frozen carbon dioxide, frozen methane, and frozen ammonia, along with the rocky grains. Astronomers call the boundary between these regions the frost line. Inside the frost line, only rocky materials can remain solid. Outside the frost line, ices can also stay solid. This is why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are small rocky worlds made mostly of silicates and metals, while the outer planets, Jupiter, Saturn, Uranus, and Neptune, are huge gassy worlds with lots of volatiles, including vast amounts of water in the form of ice and liquid. The frost line shaped the character of the planets we ended up with. But the important thing for our story is this. regardless of whether you were inside or outside the frost line, regardless of whether the material in the disk was hot rock or cold ice, everything was embedded in the same flat disk. Everything was orbiting on the same plane. Everything was moving around the young sun in the same direction. The flatness applied everywhere, at every distance from the sun. The disk was the canvas on which all of the planets would eventually be painted. And I want to pause here to emphasize just how inevitable this all is. Because when I first encountered this idea, I was struck by how clean and unavoidable the logic is. It's not that our solar system happened to be flat. It's that any rotating cloud of gas and dust collapsing under gravity must become flat. It's not a quirk of history. It's a consequence of the laws of physics. Collisions cancel out opposing motions. Opposing motions exist along the axis of rotation because particles there are moving up and down toward each other. Opposing motions don't exist around the axis because everything's going the same way. So vertical motions die and rotational motions survive. A sphere becomes a disk every time. And this isn't just theoretical. We have observational proof. Wherever we look in the galaxy and find a young star being born, we see a flat disk around it. We see it around solar mass stars like the Sun. We see it around stars much bigger than the Sun. We see it around tiny stars that are only a fraction of the Sun's mass. We see it around brown dwarfs, failed stars that never even got hot enough to ignite fusion. Whenever you have a collapsing cloud with a rotation, you get a disk. The consistency is overwhelming. We've now imaged hundreds of these disks across the galaxy. Each one looks the same. A central star, or sometimes a pair of stars, with a flat rotating plate of gas and dust swirling around it. Some are seen edge-on, like looking at a plate from the side, and they look like thin, dark lines cutting across the glow of their parent star. Some are seen face-on, like looking at a plate from above, and they look like bright circular rings. Some are seen at an angle, and they look like ellipses, but every time, once you factor in the perspective, the shape is the same. A disk. A flat, rotating thin disk. It's one of the most consistent patterns in observational astronomy. If you show me a picture of a young star, I can tell you with near certainty that it has a flat disk of material around it, because that's what the physics demands. And that's what we see every single time. And here's something beautiful. The same physics that made our solar system flat is at work at many scales. Think about Saturn's rings. They're a disk, an almost impossibly thin disk of ice and rock orbiting Saturn. Why? For exactly the same reason that the solar system is a disk. Saturn's rings formed from material that was orbiting Saturn, and any initial three-dimensional cloud of that material got flattened by collisions, just like the solar nebula did. The particles in Saturn's rings are still colliding with each other today, which is why the rings remain so incredibly thin. Vertical motions keep getting cancelled. Horizontal motions keep surviving. The disk persists because the physics that made it is still acting on it. I should also mention something I've been glossing over, because it adds an important piece to the puzzle. Magnetic fields, molecular clouds, and protoplanetary disks are not just made of neutral gas and dust. They contain charged particles too, ionized atoms and electrons that respond to magnetic fields. And the young sun, like all stars, has its own powerful magnetic field. So throughout the disk, magnetic field lines thread through the gas, coupling the motions of charged particles to the magnetic forces. These magnetic fields play a surprisingly important role in flattening the disk and in transferring angular momentum outward. As the disk rotates, the magnetic fields get twisted and stretched, and this creates something called magneto-rotational instability. Without getting too technical, this instability generates turbulence in the disk, and that turbulence acts like a viscosity. It's part of what allows gas in the inner disk to lose angular momentum and spiral inward toward the star, while gas in the outer disk gains angular momentum and drifts outward. Without this mechanism, it would be much harder for the disk to funnel material onto the growing star, and the whole formation process would take much longer. Magnetic fields are one of the unsung heroes of planetary formation. They help redistribute material, enforce the flat geometry, and keep the disk evolving in the way that eventually produces a solar system. And how long does the whole process take? From the first formation of the disk to its eventual dissipation, the typical lifetime of a protoplanetary disk is about 10 million years. That might sound like a long time, but it's actually fairly short on the cosmic scale. Within that window, the disk has to form, flatten, produce planets, and then fade away. The gas component of the disk, the hydrogen and helium, gets blown away by the young star's intense radiation and stellar winds relatively early, within about the first 3 to 5 million years. The dust component can linger a bit longer, slowly thinning out as dust grains stick together into larger bodies, and as the remaining small grains get blown outward by radiation pressure. By the end of that window, the disk is essentially gone, and what's left is the star at the center, and whatever planets, moons, and smaller bodies formed inside. Our solar system today is essentially the archaeological remnant of a disk that disappeared about 4.5 billion years ago. What remains are the planets, the moons, and the smaller debris, all still obediently preserving the flat geometry that was stamped into them during their formation. Galaxies are another example. Spiral galaxies like the Milky Way are flat, rotating disks of stars. Hundreds of billions of stars, arranged in a thin plate with a bulge in the middle, rotating around a common center. The Milky Way is 100,000 light-years across, but only about 1,000 light-years thick at its thickest. That's a disk. An enormous galactic disk. And it formed for the same reason a solar system forms. A vast rotating cloud of gas collapsed and collisions flattened it into a disk, inside which stars were born along the plane of rotation. The same mechanism at every scale, from Saturn's rings to solar systems to galaxies. Wherever you have a rotating collection of matter under the influence of gravity and friction, you get a disk. It's nature's favorite shape for organized rotating systems. Spheres belong to objects held together purely by gravity, like stars and planets. Disks belong to systems of objects held together by gravity and organized by rotation. So now we understand why our early solar system was a flat disk of gas and dust. The cloud that became our solar system started out with some rotation. As it collapsed, that rotation got amplified by angular momentum conservation. As particles moved around in the collapsing cloud, their vertical motions were cancelled by collisions, while their rotational motions survived. The cloud flattened into a disk. Thin, spinning, wide disk of material with the sun blazing at its center. But a disk on its own is not a solar system. Not yet. What surrounds the young sun is the starting ingredient, the unshaped clay from which worlds will eventually be sculpted. Inside that disk, the process isn't finished. It's just getting started. Because within this thin, spinning plate of gas and dust, something else is about to happen. Something that will transform the smooth, continuous disk into the collection of discrete, separate planets and moons and asteroids that we know today. The disk is going to lump up. It's going to collect its scattered material into concentrated bodies. And because everything happening inside the disk is happening within the plane of the disk, those bodies, when they form, will inherit the disk's geometry. They will orbit on the disk's plane. They will move in the disk's direction. They will carry the flatness forward, becoming the planets we know in the arrangement we know, for the same reason the disk itself was flat to begin with. How a smooth disk of gas and dust transforms into solid, separate planets, and why those planets remember the flatness of the disk they came from, is the final piece of the puzzle. We left off with a flat disk, a thin, rotating plate of gas and dust stretched out around the newborn sun, spanning an enormous breadth, but only a tiny fraction of that in thickness. This is the stage on which everything else will unfold. But a disk is not a solar system. A disk doesn't have planets. It has particles. Trillions upon trillions of tiny grains of dust, atoms of gas, specks of ice, all orbiting the sun in the same direction, all riding along in the same flat plane. The question now is how that featureless plate of material became the 8 discrete planets we see today. And more importantly, why those planets inherited the disk's flatness so precisely. The answer starts small, really small, smaller than you can imagine, because the first step in building a planet isn't the formation of a giant world. It's the coming together of 2 specks of dust. Picture the disk in its early days. Dust grains the size of smoke particles are drifting through the gas, all of them orbiting the sun, all of them moving in the same general direction because they're all embedded in the same rotating disk. As they drift, they bump into each other. Now, 2 particles in a vast empty volume of space almost never collide with each other. The chances are vanishingly small. But inside the dense midplane of a protoplanetary disk, there are so many particles packed into such a relatively small volume that collisions happen constantly. And when 2 dust grains drift into each other, they often stick. Not by magnetism, not by gravity, because dust grains are far too small to attract each other gravitationally in any meaningful way. They stick through a process called electrostatic attraction and van der Waals forces, the same kinds of weak molecular bonds that make dust cling to your bookshelf when you haven't cleaned it in a while. 2 dust grains become 1 larger grain. That grain, slightly bigger now, continues drifting through the disk. It collides with another grain. They stick. Now it's bigger still. And on and on and on. This process of dust grains clumping together is called accretion, and it's the first and most important step in building a planet. Over thousands of years, the microscopic grains grow into millimeter-sized pebbles. The pebbles grow into centimeter-sized stones. The stones grow into meter-sized boulders. And all of this is happening inside the flat disk, with every growing object still orbiting the sun in the same direction, still embedded in the same thin plane of material. Now, when objects get up to the scale of boulders and larger, a new force starts to matter: gravity. Individual dust grains are too small to pull on each other gravitationally. But once you have an object that's a kilometer across, its gravity becomes significant enough to attract nearby material directly. And this changes everything. Before, a dust grain had to physically touch another grain to stick to it. Now, a kilometer-sized object can reach out gravitationally and pull in material from its surroundings, sweeping up smaller objects that stray too close, These kilometer-sized bodies are called planetesimals. They are the building blocks of planets. The disk, which started as a smooth haze of gas and dust, has now become populated by millions or billions of these rocky or icy bodies, all sharing the thin mid-plane they were born from. And these planetesimals are going to do something remarkable. They're going to collide with each other over and over again, and each collision is going to produce something bigger. Now, this is where you have to think carefully about what's happening. If planetesimals are flying around a star, why don't they collide at random angles and produce objects with random orbits? Why does the final collection of planets end up on the same flat plane? The answer is almost too simple once you see it. Because the planetesimals were already on the same flat plane to begin with. They inherited their orbits from the disk they formed in. They're not flying around randomly. They're all orbiting the sun in the same direction, all in the same plane, all riding along on the same rotating surface that the disk established long before. When two planetesimals collide, they're colliding with each other at similar orbital speeds and similar orbital inclinations, because they're both traveling through essentially the same rotating structure. Think of it like this. Imagine a highway where every car drives in the same direction at roughly the same speed. If two cars bump into each other, it's a gentle tap, not a head-on collision. They're both going the same way, and the collision is a soft sideswipe. The two cars might stick together, merging into a single larger vehicle, but the merged vehicle is still going in the same direction, still on the same road, still in the same lane. That's what was happening in the protoplanetary disk. Planetesimals were colliding constantly, but almost all the collisions were gentle because everyone was traveling in the same direction. When two planetesimals merged, they formed a larger body that inherited the average motion of the two original bodies. And that motion was, almost without exception, motion in the plane of the disk, in the direction of the disk's rotation. So as planetesimals merged into larger and larger objects, those objects remained on the plane of the disk. They couldn't help it. Every single collision that built up a planet reinforced the flatness, and the process kept going. Planetesimals a kilometer across merged into bodies 10 kilometers across. Those merged into bodies 100 kilometers across. Those merged into bodies 1,000 kilometers across. We call the bigger bodies planetary embryos, or protoplanets. And by this point, we're looking at objects massive enough to have meaningful gravity. Objects that can sweep up smaller planetesimals over large distances. Objects that are well on their way to becoming planets. Inside the inner part of the solar system, inside the frost line, where it was too hot for ices to exist, the planetary embryos were made of rock and metal. They grew to the size of Mars or Mercury. Eventually, the biggest embryos collided with each other in a series of spectacular impacts that happened over tens of millions of years. Mars and Mercury stayed about the size they'd reached. Venus and Earth merged with their neighbors and grew to their current sizes. All of this assembly, without exception, took place in the plane of the disk, because that was the only region where building materials existed in any meaningful concentration. Outside the frost line, in the colder outer regions, the embryos had access to water ice and other frozen volatiles, as well as rock. They could grow larger, and once they reached about 10 times the mass of Earth, their gravity became strong enough to pull in the surrounding hydrogen and helium gas directly, turning them into gas giants. Jupiter formed first, then Saturn. Uranus and Neptune formed farther out, where there was less gas available, so they ended up as ice giants rather than true gas giants. But again, all of these planets formed within the plane of the disk, in the direction of the disk's rotation. The result, after about 100 million years, was the solar system we recognize today. 8 planets, all orbiting the sun in the same direction, all on nearly the same flat plane. Because they all formed inside a flat rotating disk, they all inherited that disk's geometry. They couldn't have ended up any other way. And notice something important. The inheritance goes even further than just the planets themselves. The planets are rotating too, most of them in the same direction as their orbital motion. Their rotation also came from the disk. As material collected into a growing planet, the angular momentum of that material accumulated as the planets spin. That's why most planets rotate in the same direction they orbit, on axes that are roughly perpendicular to the plane of the disk. The same physics that flattened the disk also tilted the planet's rotational axes to match. The major moons of the planets followed the same pattern for the same reason. Jupiter, Saturn, Uranus, and Neptune all had their own mini-disks of gas and dust surrounding them during their formation, left over from the material they were pulling in. And inside those mini-disks, moons formed in exactly the same way that planets formed in the solar nebula. Particles accreted into larger bodies, which accreted into still larger bodies, which became moons. And because the mini-disks were flat, the moons that formed inside them orbit their parent planets on nearly flat planes, in the direction of the mini-disk's rotation. Jupiter's 4 large moons, Io, Europa, Ganymede, and Callisto, all orbit Jupiter in almost exactly the same plane. Saturn's large regular moons do the same. It's the same process at a smaller scale. Flat disks produce flat moon systems, the same way they produce flat solar systems. And it's worth pausing on Saturn's rings one more time, because they deserve special recognition. No other structure in the solar system preserves the ancient disk geometry as purely as those rings do. Every particle in them is obeying the same rules that flattened the original solar nebula, still colliding, still cancelling vertical motions, still keeping horizontal ones. The rings are not just beautiful, they are a working demonstration of disk physics, frozen in action around Saturn. Saturn's rings are a living example of the exact physics that flattened the solar nebula, still operating today, still enforcing the same geometry, still producing the same razor-thin disk because the rules of physics demand it. So when you look out at the solar system and see the planets arranged on a plane, you're not seeing a coincidence. You're seeing the direct fingerprint of the rotating disk they formed inside. You're seeing the geometry of the disk, preserved in the orbits of the worlds that grew from it. It's almost like the solar system is a fossil of the cloud that used to be there. The planets are the pieces that solidified out of the disk, and the arrangement of those planets still carries the shape of the original structure. Now, I said earlier that the planets are not all perfectly aligned, and that's true, and it's important, and I want to talk about it now. Because one of the most beautiful things about science is that a theory should not only explain the main pattern, it should also explain the exceptions. And the exceptions to the flatness of our solar system turn out to be just as revealing as the flatness itself. Let's start with the numbers. I gave some of these before, but let me pull them together. Mercury has an orbital inclination of about 7 degrees relative to Earth. That's the biggest of the 8 planets. Venus is at about 3.4 degrees, Mars is at 1.8, Jupiter at 1.3, Saturn at 2.5, Uranus at 0.77, Neptune at 1.77. So the planets are not exactly on the same plane. They're close, but they're not identical. There's some scatter. A few degrees here, a few degrees there. Why? If the physics I've been describing really does produce a perfectly flat disk, why aren't the planets on a perfectly flat plane? The answer is that the solar system didn't stay the same after it formed. It's been evolving for 4.5 billion years, and over that time, various things have happened that have slightly tilted the orbits of the planets. Here are some of the main causes. First, the planets interact gravitationally with each other. When two planets pass near each other in their orbits, their gravity tugs on each other. Usually these tugs are small, but they accumulate over billions of years. Over long time scales, they can slightly alter the inclinations of orbits. Mercury is especially susceptible to this because it's small and close to the Sun, where its orbit is most easily perturbed. Over long time scales, Mercury's orbit wobbles noticeably. Second, the early solar system had many more objects than it does today. In the first few 100 million years, countless planetesimals and planetary embryos roam the disk, crashing into things and getting flung around by the gravity of the big planets. Jupiter especially sent material flying in all directions. Some hit the planets and jostled their orbits. Some got kicked out of the solar system entirely. Some ended up in the asteroid belt or the Kuiper Belt. The effects of this early chaos are still visible today. Third, giant impacts. During the early days, planets were not just forming by gentle accretion. They were also being slammed into by massive objects. Earth's moon is believed to have formed when a Mars-sized body collided with the young Earth. That kind of impact would have dramatically changed Earth's orbital tilt and rotation. Other planets experienced similar events. These catastrophic collisions left lasting fingerprints on the orbits and rotations of the planets. Fourth, the gas disk itself didn't last forever. It eventually dissipated, blown away by the young sun's radiation and stellar winds within about 10 million years of the sun's formation. While the gas was still there, it acted like a dampener, smoothing out orbital variations and keeping the planets on a very flat plane. Once the gas was gone, the planets were more free to drift, and their orbits could start to evolve under the influence of their mutual gravitational interactions. The small inclinations we see today are the accumulated result of billions of years of gentle drift. So the fact that the planets have small inclinations rather than perfect ones is exactly what we'd expect. A solar system that starts out perfectly flat then evolves over billions of years with all sorts of gravitational interactions and giant impacts should end up with planets that are still close to the original plane but not exactly on it. A few degrees of scatter is precisely the kind of scatter you'd predict. Much more than that would be a problem for the theory. Much less would be almost impossibly neat. What we see is exactly right. Now, there are some much bigger exceptions in the solar system, objects that are way off the plane. Pluto is the most famous. Pluto's orbital inclination is about 17 degrees, more than twice the inclination of Mercury. That's a significant tilt. And Pluto isn't alone. The other dwarf planets in the Kuiper Belt, the region beyond Neptune, have a wide range of orbital inclinations. Some are on the plane, but many are tilted by 10, 20, even 30 degrees or more. The Kuiper Belt as a whole is much thicker and much more disordered than the region of the planets closer to the Sun. And beyond the Kuiper Belt, things get even stranger. There's a region called the Oort Cloud, which extends from about 2,000 astronomical units out to roughly 100,000 astronomical units. The Oort Cloud is believed to contain trillions of icy bodies, and it's the source of most long-period comets, the ones that swing by the sun once every few thousand or few million years. And here's the thing, the Oort Cloud is not flat, not even a little. It's a spherical shell. The comets that come from it can approach the inner solar system from any direction, at any angle. Some come in over the top of the solar system. Some come in from below. Some come in at wild tilts. There's no preferred plane for the Oort Cloud at all. Now, this might seem to contradict everything I've been saying. If the whole solar system formed from a flat disk, why is the Oort Cloud a sphere? Why is Pluto tilted? Why aren't all Kuiper Belt objects perfectly on the plane? The answer is that those regions have been disturbed violently over the age of the solar system. Pluto and other Kuiper Belt objects formed in the flat disk, like everything else. But the Kuiper Belt is far from the Sun, where the disk was less dense and where the gravitational influence of Neptune has been significant. Over billions of years, Neptune's gravity has stirred up the Kuiper Belt, flinging objects into tilted and stretched orbits. Pluto in particular is in a resonance with Neptune, a specific orbital relationship that has elevated its inclination over time. The Oort Cloud is an even more extreme case. The objects in the Oort Cloud are so far from the Sun that the Sun's gravity barely holds onto them. At those enormous distances, the gravitational influence of passing stars, and even of our own galaxy, becomes significant. Over 4.5 billion years, passing stars have gently tugged on Oort Cloud objects, gradually scattering them out of the original flat disk into the roughly spherical shell we see today. The Oort Cloud is flat in its origin, but disturbed beyond recognition by external gravitational influences over cosmic timescales. So the exceptions aren't really exceptions at all. They're exactly what you'd expect given the physics. The inner solar system, where the Sun's gravity dominates, remains close to its original flat geometry. The outer solar system, where other gravitational influences have had time to scatter things around, has lost some of that original flatness. The gradient from very flat near the Sun to less flat far from the Sun is itself a fingerprint of the disk origin. A randomly arranged solar system wouldn't show that pattern at all. It would be scattered everywhere. Our solar system shows flatness where flatness is preserved, and scattering where scattering is expected. Both support the same underlying story. There are also a few objects with extreme orbits that stand out. Some comets orbit the Sun in the opposite direction from the planets. Some asteroids have been flung into highly tilted orbits by encounters with Jupiter. But these are always the small, less massive objects. No planet orbits the Sun backwards. No planet is on a wildly tilted path. The major bodies, the ones that represent most of the mass in the solar system after the Sun, all share the plane. Small objects can be kicked around by gravitational interactions, but the big ones hold their positions. The signature of the original disk is clearest in the most massive members of the solar system, which is exactly what you'd expect. And now, as we come to the end of this story, I want to zoom out and think about what this all means. Because our solar system is not unique. Every planetary system forms the same way. Every star is born from a collapsing cloud, and that cloud has rotation, and that rotation forces the material around the new star into a flat disk. And inside that disk, planets form. The flatness we see in our solar system is not a local peculiarity. It's a universal feature of how planets come into being. When astronomers look at other star systems in the galaxy, they find the same pattern. The exoplanets we've discovered, the ones we've characterized well enough to measure their orbital inclinations, tend to orbit their parent stars on flat planes, in the same direction their parent stars rotate. There are exceptions, of course. Some systems have been disturbed by close encounters with other stars, or by gravitational interactions between planets, just as the outer regions of our own solar system were. But the default pattern, the one that shows up again and again, is flatness. Planets form in disks, and they remember the disks they came from. Every solar system, anywhere in the universe, carries the signature of its birth. And that signature is a flat plane. It means that if you could somehow travel to another star system far away in the galaxy, you would most likely find it arranged the same way ours is. A central star, planets orbiting on a common plane, moons circling those planets on planes of their own. The shapes would vary. The numbers and sizes of the planets would be different. Some systems would have gas giants enclose. Some would have Earth-sized worlds scattered through their habitable zones. But almost all of them would be flat, because the physics of forming a planetary system produces flatness. Always. And that brings us back to where we started. To the night sky. When you look up and see Jupiter, Venus, and Saturn lined up along the same invisible band of sky, when you trace the ecliptic from horizon to horizon and realize that every planet you can see follows that same path, you're seeing the echo of something that happened 4.5 billion years ago. You're seeing, in real time, the aftermath of a collapsing cloud of gas and dust that rotated and flattened and birthed a star and populated its plane with worlds. The geometry you're witnessing is not a coincidence. It's not a design. It's the inevitable result of gravity, rotation, and collisions working together in the most efficient way the universe knows how. You live on one of those worlds. You were born on a planet that formed inside that disk, alongside 7 others, all of them still tracing their ancient circles in nearly the same flat plane they inherited from the cloud that gave them life. When you stand outside on a clear evening and watch the planets rise and set in a neat line across the sky, you're not just observing a curious pattern in nature. You're looking at the preserved shape of the cradle you came from. The cloud is gone, the disk is gone. The sun has been burning steadily through eons of cosmic time, erasing most of the traces of where it came from. But one trace remains. The flatness, the ecliptic, the plane of the planets. It is the last standing evidence of how we came to be here, and it's right there above you every night, if you know where to look and what it means. And now, you do.